rest of the day, I wanted to just take an opportunity to kind of walk through some of the ideas that brought this event together and provide some context that I hope will be helpful. It was certainly helpful for me to kind of engage with some of these concepts, and I'm hoping that this sets a useful context for the day and talk a little bit about why we're excited about ST2110 at PIXERA, because we see it unlocking a whole universe of creative possibilities and economical new workflows. The premise of my presentation is that there is a growing interest in these concepts within our industry. There are mega projects that are being realized with ST2110 at the core, that there's still some ambiguity, some uncertainty. I know that I've certainly had some conversations at trade shows and amongst partners and clients where there's some uncertainty or maybe some misconceptions about what's happening and what technology is what. So I'm trying to sort through some of that with my presentation. And the last premise is that the people in this room are the ones who have the agency to kind of oversee this. So it's not going to be like the dictate from on high that you have to do this, right? It comes down to does it make more sense? Does it provide a better workflow? Is it more cost effective? So it comes down to the manufacturers and the service providers in this room. So we'll go through the background of AV Stumpfl a little bit, talk about the different standards that are coming into place, and specifically the signal theory underneath the switchover of the substrate, which we'll talk about, and then also why IP is better with specific examples, and then finally our approach at PIXERA. If you haven't heard the story of AV Stumpfl, it is a 50-year-old story now, so this is our 50th year. Reinhold Stumpfl started the company in his attic, tinkering around with Leica slide projectors, and that has evolved to a multinational tech company with offices across the globe, multiple product lines, including our projection screens. This is one here, as well as our media server line, PIXERA. We have offices in Austria, in London, here in Santa Monica, and then in Atlanta. And PIXERA is really a real-time media processing platform for large pixel spaces. It's real-time, it's 3D, 64-bit. It's able to manage audio, video, lighting data for really large installations that have really complex technical requirements or operating environments, and maintaining a really user-centered approach to the design of the interface and the product as a whole. We design and build our own hardwares to run our software platform on, which maintains a really high level of quality and reliability and consistency. We also offer PIXERA as a software-only solution for customers where that makes more sense. And then we also really bring ourselves into our clients' projects. We're not just that mercurial company that releases new versions every 6 months and says good luck. We definitely are involved really actively in R&D, in specification, training, all of the things that come with a platform as kind of multifaceted as PIXERA. Car shows. Car shows are very much part of the history of AV Stumpfl and of PIXERA, because the German car show industry was doing super high resolution, super high fidelity, high frame rate, high color bit depth playback across distributed rendering systems way before it was cool. They were all trying to one-up each other, keeping up with the Joneses, and the PIXERA render engine was really cut its teeth in this environment where we were always trying to push the boundaries of what was possible with fidelity, reliability, stability, and synchronization across multiple servers at the core. So that render engine remains one of the pillars of the software, along with the user interface, which we designed to be as approachable and as user-friendly as possible. And you'll see that it is very intuitive, but also keeping in mind that it's not right for everybody. And that's why we make our APIs as robust as they are. So that if you have another piece of software, or you want to write your own software or your own plugin, all of the hooks are there for you to do that. And if it's not there, we can typically add it if there's enough of a rationale. So those three pillars are really the forefront of what we do. And that software-focused, user-centered philosophy is really one of the big reasons that we're excited about ST2110 as our workflows become more and more software-defined. PIXERA has been used on massive shows, Metallica, Adele, League of Legends and Valorant World Championships, Chris Stapleton's tour, all HDR, airports, lobbies, interactive, immersive, and generative art pieces running in PIXERA. Virtual production has been a huge area for us recently, and projection mapping has always been something that we've been good at. So that's a little bit about PIXERA, and now I want to talk a little bit about some of these video or AV over IP concepts, and hopefully set some useful context for the day. So I titled my slide deck, Pure Pixel Data and Software-Defined Workflows. So I think it's fair to define those right off the bat. Pure pixel data is kind of an idealistic term that I've come to use in my mind as this kind of North Star of what would be really great if we could get there. Now, the idea behind pure pixel data is that because the history of video is analog and the history of audio and video transmission is analog, we are still constrained by a lot of analog heuristics that include, serial transmission of data across waveforms and the interpretation of that data using hardware-based solutions, attenuators and antennas and things like that, and decoders. And the idea is to eventually get to a place where the content or the data for the video and audio is as unconstrained by those concepts as possible. And the software-defined piece is just the idea that if you can reach that idealistic state where your data is in its purely encoded form at high bit depths, then all of the interventions that you make on that data can be done in software and don't require specialized, expensive, esoteric hardware. It just becomes a couple lines of code. Lots of other industries have already seen this transition, the transition into the IT world, and I think that's just where we're headed, and you'll see in the rest of the presentation today, it's a lot of networking. Quickly introduce some of these concepts, bring some concepts to life with examples, and explore some different efforts underway. So just to restate the thesis of the whole vibe here is that this transition is better. It offers better workflows. It offers more flexibility, more scalability, more economical workflows that allow us to do more projects, bigger projects, with ultimately less complexity and less cost. Using video or using visuals as the primary concept, I don't mean to leave audio behind, but I do think that using video data, because its bandwidth requirements are so much higher and it's a little bit more of a visual medium, it helps to explore these concepts a little bit using visual data, but all of these concepts apply to the transmission of audio data as well. The mission is really to capture or create content in as high fidelity a format as possible, using state-of-the-art softwares or sensing equipment, transmit that to some kind of processing environment where you can make interventions, you can interact with that content creatively or to reformat it for different endpoints, and then to transmit it to a reproduction device like a projector or a screen or an AR headset or whatever that might be, while destroying as little of the fidelity as possible through that process. So you see companies like Panasonic and others are developing insanely sophisticated visual sensors to be able to take analog waveforms and from the world and encode them in digital bits. And then you have softwares like Cinema 4D and Unreal that allow you to generate photorealistic environments in software at high color bit depths. You then have other softwares that allow you to interact with this content, this camera footage, or these virtual worlds in real time to be able to color grade or create interaction with users. And then you can display this content or this data on really high-end displays. So you've got these amazing sources, processing nodes, and endpoints, and we want to find a way for the go-between, the transfer of the data between them to be as least destructive as possible. In the past, we used analog waveforms and then SDI, which are both serial transmission, which means that it's linear, it's continuing always nonstop, and in many cases the audio and the video are grouped together, and you need to use legacy analog concepts like sync pulses or blanking intervals when you're transmitting that data. So you have all of your data grouped together, traveling as a continuous stream, which makes it much more difficult to route, to process in a parallel way, or to replicate or in any way transform. Typically, in the past, we needed things like FPGAs or application-specific integrated circuits because they were the only things that could offer low enough latency, high enough bandwidth, reliability, and cost effectiveness to be able to realize our workflows in the Pro AV space. There were downsides to this, as of course we all know. You know, everybody's waiting for that next card-based solution. You've upgraded your cameras, and now you need your switcher to follow suit because the cards that you bought 3 years ago no longer support those new video formats or that new resolution, and you're tied to the update cycle of that hardware manufacturer. It's not as flexible. I mean, these FPGAs, you can do distribution amplification or scaling operations, but as compared to something that you could do with a Python script or some other software-based intervention, you're way limited. Another advantage of these legacy technologies is that the workflow kind of emerges from the system design. So if you look at an SDI or a DisplayPort or HDMI-based signal diagram, you can kind of figure it out what's going on, reverse engineer it just based on the line diagram. And if you take a device that's rated for the right format and you plug it into another device, connect the BNC, it turns on. And that is a very comforting thing, and it is very important when you're trying to scale up these systems, because you can't expect everybody that interacts with the system you design or implement to have network engineering abilities to open up a Wireshark or open up PowerShell and figure out what's going on that way. But there are people that are solving those problems in the software space. So the big point I try to make is that there's a lot of focus that I think naturally goes on the substrate. Switching from XLR, switching from DisplayPort, from SDI, XLR, or sorry, BNC connectors over to copper and fiber. At least that's certainly like when I started engaging with these concepts, like, okay, instead of an SDI switch, it's a network switch. Instead of an HDMI cable, it's a copper cable or a fiber cable. But that doesn't really go deep enough to understand the implications of the switchover, because the nature of the data itself is changing. It's becoming packetized, and it's becoming asynchronous. And that has been already done in the internet, right? So I certainly thought, okay, well, we've been doing video over IP for a long time, right? Cat videos, YouTube, early streaming sites, and in fact, there's already been attempts inside the Pro AV space to bring the advantages of AV over IP into reality. SDVOE, HD-based-T. When I started this industry at an integrator in Minneapolis, I think the first week, my boss was like, here's a laptop, go figure out what AV is. And we were an AMX dealer, so I went on AMX's university and I started learning about their JPEG 2000, AV over IP, and they were talking about the AV IT convergence and how it was imminent, and it was going to be the take over the whole industry. And that was 10 years ago, and of course we know where that is. I think the website that talks about JPEG 2000 on the AMX is some buried deep in the Harman pages. But anyway, these attempts have existed, but none of them have really had the juice. And I think there's a couple reasons for that. They weren't ambitious enough, they weren't open enough, and they didn't include a standards process that really included everybody. And they weren't all high performance enough. And what I mean by high performance is we're dealing with extremely high data rates. We're dealing with a need for extremely low latency. We need to synchronize across n number of nodes. And we have zero tolerance for fault. We can't blip to black. We can't lose a frame. We can't tear. That's not acceptable in our world. And these technologies have to be ambitious enough, reasonable infrastructure costs, which is a little bit of a stretch, but it's getting there, and then open standards with low or no licensing costs. So to solve all these problems, it's not just one standard, it's actually a family of standards. And we're going to go into these in different levels of detail in different people's presentations. But the standards that really get discussed the most are ST2110 from SMPTE, PTP, NMOS from AMWA, and IPMX from AIMS. And if you look into these standards, you can actually see that they, in turn, are based on standards, which are, in turn, based on standards. So we are, several orders up from the base standards. If you know RTP, the RFC 3550 standard that defines real-time packetization for IP transmission is really what all of this is built on. And from there, you get things like the TRO3, which is the uncompressed streaming of content over the network, which was the basis for ST2110. And you have ST2022, which handles compression and also redundancy. There's a lot of standards, and in fact, you can read them. They're just PDFs that are available online. One of the big innovations of 2110 is that it separates audio, video, and data into separate streams, into separate essence streams is the terminology that they use, which can all be timestamped separately, routed separately, replicated, transformed, intervened on separately. 2110, what is it? Well, it's actually just like 9 PDFs. That's what ST2110 is on one level. It's a standard, and it's available. You buy them each. They're $50 each. If you really want one, I can print one. We bought them. But the highlights, some of them are fairly esoteric and are not as interesting to me anyway, but the highlights are the -10, which is the PTP, so it defines timing on these networks, -20, which is the uncompressed video standard, 30 is audio based on AES-67, 21 is the network shaping, which is really important and provides that ability to use large distributed networks and multicast to get these packets where they need to go. And then the -40 is the ancillary data, which has a ton of really exciting implications. Here's an animation from Wes Simpson. He's a SMPTE heavy hitter who's done a lot of the early kind of education on this. It's really helpful in my journey. It shows how the different essence streams are packetized. Okay, so when we look at the legacy of FPGA or application-specific chips being the basis for parallelization and low latency transmission and processing, well, there's new alternatives, and some of those alternatives are at the processing level. So we've taken advantage of the massive economies of scale of GPUs that have been afforded by video games and now AI. The high bandwidth transmission, we no longer need big card-based solutions. We have switches. The synchronization is no longer tri-level blackburst or frame sync. It's PTP, and the low latency and zero fault tolerant transmission of high bandwidth data is defined in ST2110. And then the next layer above this to make this more usable and less science experimenty is NMOS for control and IPMX for, I would summarize and say, plug and play level functionality. PTP, which Michael Kohler will give you a doctoral dissertation in later today, is a really cool technology that essentially allows us to maintain really stable, precise, and accurate timing across large networks of electronic devices. The main two thresholds that I sought out when I was learning about the accuracy and precision of PTP are, what's the lag interval between audio and video sync, where it becomes noticeable by a human, and it turns out that's around 20 milliseconds, worst case scenario. And what's the interval of time that two computers can stay in sync presenting frames on something like an LED screen? And I looked to the QuadroSync manual, and they defined their tolerance as 50 parts per million, which at 60 hertz calculates to 0.0012 hertz, which I calculated to be 1.2 milliseconds. Now the good news is PTP can synchronize within 1 microsecond. So we're orders of magnitude more precise than we even need to be for our most common applications. PTP is used for high frequency trading and chemical research and all sorts of stuff that has much higher accuracy than us. So what does NMOS do? Well, NMOS does two primary things at this moment. It says it provides an API for devices to say, hi, I'm a source, and register themselves on the network as a source with a certain resolution, a certain frame rate, a certain color space, and then saying, hi, I'd like to go to that display, and I'd like to go with my buddy, and I want to go in 2 seconds, or I want to go in 2 minutes. So it allows you to do individual or batched, switching operations either on instantaneously or on a schedule. And that's the ISO4 and ISO5 part of the NMOS standard. So IPMX, what is IPMX? Well, it is an attempt by an organization called AIMS which you can join for like $3,500, and you can go to the meetings and have your little vote on what IPMX is. And it's an attempt to kind of bring these standards a little bit more into the mainstream by doing things like relaxing the timing requirements so you don't need PTP anymore, by adding compression so that you're not always dealing with uncompressed video or audio data, adding things like HTC compliance, EDID support, and ultimately things like USB so that you can add KVM functionality over that same single network pipe, excuse me. So IPMX is very much in progress. I just talked with them at ISC, had a really good discussion. Matrox, their head of hardware, is one of the main people on the AIM's board, and they're basically meeting around NAB to decide the 8 or 10 criteria things that you need to hit to say I'm IPMX as a product. So that's coming. We're excited about that. PIXERA may not be a day one adopter because it's going to require some serious development, but certainly something we're excited about and we have on our radar. How will this all manifest? Well, it really comes down to the manufacturers, the service providers in this room. Part of the reason I wanted to give this presentation, we're excited about it. We're trying to get other people excited about it as well. And I don't think it's all going to come overnight. I think it's going to come in 3 primary stages. The first is what I call spicy NDI, and that's essentially already in use. We have customers that are already using ST2110 to transit texture data between PIXERA nodes and Unreal nodes, but they're still outputting to their endpoint using traditional DisplayPort or SDI and using sync via BNC or Genlock, and then all of the sources are still, using that legacy equipment. But the internal transport, the kind of the core of the system, is using ST2110 to do that synchronized high bandwidth transmission that NDI can't support at high color bit depths. The middle out is this idea that the core of the system will find the support first, and then it will work its way into the display endpoint. So you're starting to see the LED processing companies are adding support. Megapixel is going to talk about the amazing progress they've made there. The camera manufacturers are starting to add it. You're starting to have the authoring tools like Unreal that are supporting it, so that the core of the system outwards is now going to add that support. And then finally, when the the critical mass of all the rental houses that have invested in the switches and the media servers and the cameras that have this, and there's been enough people that have done their training as network engineers, and the manufacturers themselves have had the time to integrate these products, over that 5 or 10 year time scale, and you start to see that middle of the bell curve move across that line where the average project has some kind of ST2110 involvement. I see that as the kind of the last stage. Okay, and I have to race through this because I have just a few minutes left, but I did want to kind of take some of these buzzwords and try to use really fancy, mid-level fancy PowerPoint animations to try to bring them to life. So you hear virtualization, automation, last mile object-based compositing, commercial off-the-shelf networking hardware, hit list redundancy, right? These are all the buzzwords you hear. So I wanted to take a second to say, what the hell does that actually mean? Well, virtualization is something that gets used all the time in other industries, and I think there's other products like Isaac from our friends at Smart Monkeys that are virtualizing control systems that have a lot of benefits, because in our world today, if you ask me, I have different displays and I need to render to them. Well, you start to look at each endpoint as its own, needing its own kind of compute. But because ST2110 allows you to send audio, video, and data across longer distances with no signal degradation and remain in sync, you can start to centralize those compute resources. I wouldn't say in the cloud. You're not thinking about some data center in Iowa hosting your content, but let's say you own a conference center, right? You don't need a server in every room anymore. You can have an IDF at the core of the building that hosts all of your compute, and that you can then transmit to the rooms on an as-needed basis. So you're only paying for this compute that you're using at one time. It also allows you to scale your compute independently, so that if you need a lot of real time one day, but just a lot of camera switching the next day, you can use the right hardware in the right context. Survivability, so this is a traditional video signal chain from the source through some kind of encoder, decoder, or switch, and then out to the display port. This is a redundant system where you have two different paths. You can add a separate source on the other path so that it's isolated. What 2022-7 and now 2110 add is a level of intelligence that you can program into the switch that will detect when a failure event has happened and a stream no longer exists. You can report that back upstream, and then you can program switching activity to happen that can all happen in milliseconds so that the viewer isn't any the wiser. Here's a software-based workflow that was developed by our friends at Lux Machina for the Valorant World Championships. Its idea, that if you keep everything in software, you can automate your way out of a lot of manual labor. And that was done with a game data API called Barracks that took live data from Valorant, transmitted it via OSC to a PIXERA control instance, which then triggered Notch-LC playback on the IMAG on the LED screens in the venue. So by keeping everything in software and not relying on a board or switcher, we were able to take dozens or scores or even hundreds of triggering events every minute, because the game's going on, players are getting kills, throwing grenades, switching guns, and having all of that data automatically trigger things in the game. The operators were able to just sit there with their hands behind their head as the show ran itself. Self-service is another function of software-defined workflows that's really exciting, which is new functionality is no more than a plug-in away. So being able to stand up online marketplaces where plugins are available for different softwares that use things like node-based systems to solve problems. These are software-based system flows that you can build. This is MaxMSP, which is a cool example of a software that actually gave birth to Ableton, which then now bought MaxMSP's company, which is kind of cool. So the idea is, if you need something, you go out and you download it. This Leader SDI scope, which is many thousands of dollars, is now a $5 Wireshark plugin which you can download online to analyze an ST2110 stream in software. Okay, so this is the last one I really want to spend a little time on. I might go a little over, sorry Tavia, but I want to make sure to talk about this because this is what the sandwich is all about. Last mile object-based compositing. So in the past, if you would have come to me and said, I want to have this immersive experience with all of this LED or all these projectors, there's 8x 4K, I would say, well, you would need many real-time servers and many LED processors, and you would need a matrix to send that camera for that immersive experience across that network in order to be able to put the real-time content and the camera feed anywhere in that room at any given time based on where the person was moving. With ST2110, you can take that essence stream, the video essence stream, transit it directly to the compositing server, or you could even go directly to the processor so that the camera feed goes up on the wall. A proxy of that video could go to a real-time processing node, just one, not four. It could generate the particle system that could then be transmitted over the network to the correct compositing node and then put on the screen. So the average cost per server goes down and the number of overall servers in your system goes down. Ancillary data is defined in, I think, -40 of ST2110, and currently it's limited to just HENC and VENC, but with IPMX they're attempting to add format independence and bandwidth independence for the data, which means that you could transmit things like camera and lens metadata or mesh or UV coordinate data along with the texture data so that you can stream 3D objects basically in a cool iteration of this. And finally, all of this card-based, FPGA-based, application-specific hardware gives way to GPUs, DPUs, which are the ST2110 streaming cards, and switches and fiber optic or copper cable, which, again, still carry considerable cost and expense, but they are still following Moore's law, which is going to continue to provide, more economical solutions for us. So ultimately, when you boil all of this down, it's a lot of network engineering, and you'll hear plenty of that today, and the user experience for the software control layer. And that brings us back to our approach, really being centered around the user experience of our products. So we continue to maintain the same commitment to stability in our render engine, the usability of our interface, and the openness of our APIs. We've applied that to our ST2110 implementation, which is using the RiverMax SDK with the Mellanox Bluefield card. You have access to the full 100 gigs. There's no software imposed limit on the number of streams. You can assign the stream just like any other. There it is in PIXERA 4, which we have several of these over here. You can generate a stream right from the mapping tab, just like DisplayPort or NDI. You can assign it to a screen object. You can actually write an SDP file from inside of PIXERA. And you can participate in NMOS. So these are features that we're adding to the platform here in the near future. So that is my presentation, and I hope that it was helpful.